All right, good morning. You guys have about 5 minutes to go through and fill in the reagents for these. So I've given you guys the products. I want you to go through and fill in how to make them.
I couldn't go to bed till 3 o'clock, but I was also on.
God damn it, these fucking people.
All right, so this first one here, we are doing a alkylation reaction. So in order to do so, we're going to have to pull off our proton from our alkyne. We're going to throw in a base like NaNH2. This is going to make our negatively charged alkyne. Focus a little better. Yeah. And then we need to add on these 3 carbons. So we'll need a 3-carbon chain with some sort of leaving group. Any halogen will work. I tend to like iodine for whatever reason. Looking at this next one here, we have an alkane with nothing on it, which means we're going to have to do some sort of radical bromination. So in order to do that, we are going to need to throw in Br2 because we're brominating. We don't have to see all over here. And we're also going to need an initiator, so we're going to throw in light. I'm going to jump around and do these 2 at the end. So this one is pretty similar to our one on the top left here. Our first step is going to be the same. We need a base, so throwing in NaNH2 here will let us generate our negatively charged alkyne. And then we've got this 6-membered ring with a carbon here. So we're going to need some sort of 6-membered ring with a carbon and a leaving group. I'll put chlorine this time. Doesn't matter which halogen you use. We're doing an anti-Markovnikov addition to an alkene on this middle one here. So we're going to need HBr. And anti-Markovnikov, so we're going to need a radical initiator for this one. So this is going to be in peroxide. Okay, moving on to these bottom 2. So these are going to be double alkylations. Steps 1 and 2 and 3 and 4 are usually interchangeable for these. It doesn't matter which one you do first. I like to do them left to right just because that's easier for me to keep track of in my mind. So if I was to throw in NaNH2, and then I want to add this side group here, so I need 3 carbons and a leaving group. That would give me this half of my molecule. Like I said, if you wanted to add this side first, it doesn't matter. It'll give you the same thing. So adding the second half of this, I need the same first reagent, so another equivalent of NaNH2. I don't have enough space in that box. NaNH2 here. Our right side is going to be a 3-carbon with a branch, and then a leaving group. I'll put bromine. So a Br here. And like I said, these ones can go in any order. So you could have done 3 and 4 followed by 1 and 2, and it would give you the same product for these. Okay. Last one over here. Our first reagent is going to be the same. We're doing alkylations, NaNH2. I'm going to do it left to right again. So 6-membered ring with a carbon off of it. Gets us to this, and then throwing in another NaNH2. I don't have enough space in that box. We need this 5-membered ring with a methyl off of there, and then a methyl and our leaving group to get our last one. Someone in the chat said, should we have Br2 in this? Yeah, sorry, that should be Br2, not Br. Okay, and same thing for this one. You could do 3 and 4 first, followed by 1 and 2. These reactions are interchangeable because you just make the other half first of it and then add the other side of it. Any questions on these? Okay. I'm going to cover one reaction in chapter 10, and then we're going to do some NMRs. So we are going to talk about allylic brominations. Which is section 10.7. So what this is an allylic position. There's two different terms, allylic and vinylic. Allylic is something that is adjacent, like one carbon away from your double bond, versus vinylic, which we'll talk about at a later point. I think it's only one L. And that just means that it's directly attached to your double bond here. So when they say allylic bromination, they're referring to this position that is one away. So what an allylic bromination looks like is we take something like this compound, throw in NBS, which is N-bromosuccinimide. It's a 5-membered ring. Oh wait, no, that's wrong. With an amide and a bromine on it. Or a diamide and a bromine. So it looks something like this here. And really, this is just a fancy BR donor. And what it's going to end up doing is it's going to pull off one of these two hydrogens that are in your allylic position to give you a bromination in that allylic position. So you're going to be exchanging a hydrogen for a bromine. It's a radical reaction, so it's going to follow kind of our radical pathway. We're going to have an initiation. Step where this NBS is going to get hit by light. And split into two radicals. So we'll have our amide radical plus this Br radical, which we're going to use. Our propagation is going to be a little bit interesting. I'm going to do the one that the book goes through for simplicity. So our first step is going to be Br radical interacting with our alkene, pulling off a hydrogen here. This is going to give us this allylic radical here, which has resonance, and I'll kind of talk about that a little bit later. But essentially, this here is now going to react with something a little bit different. So this is going to react with Br2, and I will explain where we get Br2 in a minute. but it can react with this Br2, kicking out our product. Plus a bromine radical. This bromine radical can then get shoved back into our propagation cycle in order to keep doing this. Our Br2 actually comes from termination. So in termination, if we have two Br radicals that come in contact with each other, we can make Br2, which can then get shoved into this part of the cycle. Okay, so these can get a little bit complicated. And even this one actually has two different answers. You can also get this bromination product where you have resonance, and I'm going to kind of go over that with a different example here. So if I take this and throw an NBS, and light, we actually have, ooh, this one's gonna be I guess they're kind of symmetrical. There are a bunch of different positions that we can pull protons off of. So we can or hydrogens, those radicals. Pull a hydrogen off of these low positions. We could also pull them off of these low positions. Technically, we can pull them off of these ones also, but it's symmetrical, so it doesn't really matter, especially because we have resonance between them. So if we pull off the allylic positions on the right here, and let's do the left ones first, so it's left to right. We could generate this product. So that would be from generating this radical here. We generated this radical. We could make this bromination product. Both of these have resonance, which can lead to products here. So this first one here on the left, if this radical comes down, forms a double bond, kicks this electron upward, you can also form this radical, which can go to a product. And as well, this one, if this does resonance, comes down, kicks out. This can now form a product. So as you can see, these very quickly can start making multiple products here. Technically, you can get diastereomers at this center, and these get complicated really quickly. So these MBS problems tend to lead to a lot of different answers. I have quite a few of them on the practice problems, and we'll go through a bunch more of them on Friday. But just so you're aware, they are messy. So I'm going to kind of shift gears and talk about NMR for the rest of the day. So we're going to kind of do a crash course in NMR, cover the majority of topics that you guys are going to see. And then we'll see how far we get. I'll give you guys some to take home and kind of do, and we'll finish it up on Friday. So, NMRs. I'm going to zoom in a little bit. So NMR is a tool for identifying unknown compounds. We are specifically going to be focusing on proton NMR or H1 NMR. So instead of looking at your carbons, you are going to be specifically looking at the protons on your molecules. There are generally about 4 things I like to look at when I look at an NMR. The number one thing, especially for these, is the formula. So I'm always going to give you guys a formula. And that's going to be really useful. It's going to tell you the number of carbons you have, the number of protons, and if you have anything else that's interesting, like this bromine here. You want to look at the number of peaks. And this is going to be different than the multiplicity, which I'll talk about in a minute. So this here has 2 peaks. There's one here, one here. They all have like a number of peaks within them. But I just refer to these as peaks in general. The next one is your integration. And an integration is going to be this H number here. So this tells you how many H's are on that signal. So it's a 1H, which generally means it's going to be a CH. This is 6H, which generally means it's going to be symmetrical CH3s. I'll talk about that in a second. Your shift. So depending on how close you are to something that is electronegative, like a bromine or an oxygen, it's going to shift you further downfield on this parts per million range here. And the last thing is multiplicity. I'm struggling to spell, which is going to relate to your neighboring H's -1. So it'll be not the number of hydrogens that are on the signal, it's going to be the number of hydrogens that are 1 away from the signal. So breaking this down a little bit, I generally just start going through and writing in the number of, or what the carbon signal probably is above the integration. So this is a 1H, it's most likely a CH. It could be an OH, but we don't have any oxygens in there, so this is probably a CH. We have 6H here, which is most likely going to be 2 CH3s that are symmetrical. They're giving us the same signal. And I'll talk about a little bit why in a second. Multiplicity is something that's really easy to look at. So we have 1, 2, 3, 4, 5, 6, 7 peaks here, which means that this CH should have 6 neighboring H's. We have 2 peaks here, which means that these CH3s should each have 1 neighbor. Generally speaking, carbons that are by themselves, like a CH3 that is next to a CH2, these protons here are going to show up in your 0.5 to 2 range. This is your very like unexciting range. And for electronegative molecules like bromine, chlorines, iodines, oxygens negatives, anything that is next to those. So I'm just going to put CH3 next to X. These protons are going to be in the 3 to 4 ppm range, which is generally where you're going to start. Most of the time, you can kind of read an NMR left to right, which is kind of nice. So in this 3 to 4 range, I have one signal. It's a CH, and I'm going to start with that. So if I take this CH, I say I'm in the 3 to 4 range. I have a bromine. 3 to 4 is where I find things that are attached to things like bromine. I'm going to throw my bromine on the molecule. So I'm going to put this Br on here. I have 2 open slots now. If I look at my multiplicity, I am supposed to be next to 6 hydrogens. We don't count the one it's currently attached to. It needs 6 more. So the easiest way to get to 6 would be CH3 and CH3. So throwing a CH3 on either side would get me a complete molecule. All of my valences are filled. If I look at these CH3s, they are supposed to have one neighbor. So this CH3 is next to a CH, so that fits. This CH3 is next to a CH, so that also fits. So that all kind of comes together. I'm going to give you guys a few minutes to attempt this next one, and then we are going to go over it together. Oh, actually, I was going to do that. So you can go back and label these if you wanted. So this, I'm going to put A and B here. A would correspond to this CH. B is going to correspond to these 2 CH3s here. And that will be a fully labeled NMR if you're doing this on an exam. Okay, now take a few minutes and go to the next one. Okay, so for this first one, I'm going to go through and integrations. So CH, CH3, CH2, CH2, CH3. Just kind of gives me something to go back to and cross out as I start doing things. We have 1, 2, 3, 4, 5, 6 peaks here, so it should have 5 neighbors. 2 peaks, so it should have 1 neighbor. 4 peaks, 3 neighbors. 1, 2, 3, 4, 5, 6, 5, and 3, 2 here. Looking at our formula, we've got a chlorine. Taking a look at our signals, we got one of them in 3 to 4 range. That's probably got the chlorine on it. And I'm going to start there. So we have CH. It's probably got the chlorine on it. So I'm going to throw that chlorine on there. It should have 5 neighbors, which means that probably easiest way to make that is going to be 3 and 2. So putting a CH3 and a CH2 on either side. We can kind of take a look at our CH3s and CH2s and see which ones fit. So it generally works right to left. We'll kind of see. So this CH3, which is now completed, should have 1 neighbor to it because it's just next to this CH here. This one has 1, so we can kind of cross this guy out. That's probably the one we used. We use the CH here. There's 2 different possible CH2s remaining. They should either have 3 neighbors or 5 neighbors. If I look at this CH2 here, it's next to a CH, which means it already has 1. It can't really get to 5 because it has to be next to a CH4, and that's not a thing for this. So it has to be this one that needs 3 neighbors. So it would need to be next to another CH2. So we can cross that one out. This CH2 is supposed to have 5 neighbors, currently next to a CH2, so a CH3 would make sense to get it all the way to 5. And then this CH3 here is supposed to have 2 neighbors, and it's currently next to a CH2, so that works. Any questions on these? The more we do, the easier they'll get. So moving on from halogens to oxygens. So if you have a single oxygen, there are 4 different possibilities for what you can have. You can either have an OH, you can have an ether, you could have a ketone, someone asked a question in the chat, or you could have an aldehyde. So the question in the chat, how exactly does the second CH have 5 neighbors? So taking a look at this CH here, it is next to, on this side, a CH3, and then on the bottom here, it's next to a CH2. So adding those 2 up gives you 5 neighbors here. And then similarly, this one has 3 neighbors because it's next to a CH, and it's next to a CH over here and a CH2 here, so that would add up to it. Okay, so oxygen or alcohols are kind of easy to identify. It's this weird little like broad peak that you get on your NMR. There's one right here. It doesn't really have a multiplicity. It's not really a singlet because it's kind of like long and awkward looking. This always tells you that you have an OH. You also have a carbon here that is next to an oxygen. This behaves a lot like a carbon that's next to a chlorine or a bromine. It's going to be in the 3 to 4 range. So that's kind of useful. And then from there, you're just following your normal rules. The only thing is that we don't count this for neighboring. OHs have like hydrogen bonding and they're constantly being broken down. And so that H really isn't all the time on there. So then when we're doing like our multiplicity, we won't actually use that H as a neighboring hydrogen. So from here, you should be able to go through and kind of do the exact same thing as you did for the other one. So I'm going to give you guys a minute or two to try to solve this one, and then we will go through it together. I might write out some of the peaks here because I think some of them are hard to, like this is 9. I would have to tell you that that's 9 peaks on an exam. I wouldn't expect you to count that. So someone asked if we need to have an A and B circled like we did in the first NOR. On exams, you guys are going to have to do that. You're going to have to go through and label which peak corresponds to which one. So I'll do that for this one. It's something you guys will just kind of get used to doing. And when we go over practice exams, I'll be sure to do that for everyone. All right, so for this first one, our 3 to 4 range going to be what's attached to our OH. I'm going to start there because that's going to probably be the easiest place to start. So I kind of wrote out all the integrations and multiplicities already. So CH, CH, CH2, CH3, 2 CH3s, 5, 8, 2, 1, 1. So starting here with this CH, if I put the OH on it, it's got 2 open spots here. As we said, the OH doesn't count for your neighboring H's, so we can kind of ignore that when it's on there. It's supposed to have 5 neighbors to it, so the easiest way to get to that would be 3 and 2. So putting a CH3 on one side and a CH2 on the other gets us here. Taking a look at all of our options, we have a CH, CH2, CH3, 2 CH3s. So we're probably dealing with these 2 CH2 and CH3s because they're the only ones. This CH3 is supposed to have 1 neighbor. It's currently next to the CH. So cross that guy out. This CH2 is supposed to have 2 neighbors. It currently is next to the CH. So it has 1 slot that's still open. So that has to be the other CH in order to get it to 2 neighbors. And that would be this other CH. Here, that CH is supposed to have 9 total or 8 total neighbors. Currently at 2 from this CH here, CH2 here, so it needs 6 more, which should be symmetrical CH3s. And they're supposed to have 1 neighbor and they're both next to the CH. I'm going to go through and label them. So A, B, C, D, E, F here. A is going to be our CH that has this OH attached to it. B is the OH. C is going to be our other CH here. D is our CH2. D. E is our CH3. And then F would be our 2 symmetrical CH3s here. I'm just gonna do the next one because the next one's kind of hard. This is an example of, so if you have, oops, something like this here. I don't know, I'll put a chlorine on here. This position here has 4 bonds to it. There is no proton here, which means that there is no signal on this molecule, or sorry, on this particular position here. So this is something that happens from time to time where you get a carbon that has no signal to it. The only way you really know it's there is you have an extra carbon in your NMR and you have a singlet. If you have a singlet, that means it has 0 neighbors, which means it has to be attached to something that has 4 bonds to it and doesn't have a proton anywhere. So if I take a look at this molecule here, I've got this broad looking odd signal. This is my OH. I've got a regular CH, 2 CH3s, 2 CH3s. This has, I think this is 7 peaks. That's another one I'd have to tell you. 1, 0, 2, 1 here. And there is nothing that is a carbon in this 3 to 4 range. And what that's going to tell you is that you're missing carbon because we have 1, 2, 3, 4, 5 carbons here. We've got 6 in our formula. We've got a singlet. That means that whatever attached to this OH has no hydrogens on it. So it would look like this. And then from here, we're kind of filling in normal. So this singlet means it's attached to the thing with nothing on it. So we'd have to put these 2 CH3s on either side here. They have 0 neighbors. This is next to a carbon with nothing on it. This is next to a carbon with nothing on it, so that fits. We can't put our 2 symmetrical CH3s here because there's only 1 slot open, which means we have to put our CH. It's supposed to have 6 neighbors. Currently it has 0. So the other set of CH3s would fit there. So this is a bit of a harder alcohol example where you start dealing with missing carbons or missing signals. I'm going to move on to ethers, and then I'm going to explain ketones and aldehydes and have you guys do them on your own, and we'll talk about them at the beginning of Friday. So, an ether is really similar to an alcohol, except you don't have this H here. Instead, you have 2 carbons on either side. So this was in the 3 to 4 range. Now we have 2 things that are in that range. So if you have an alcohol, or sorry, you have an oxygen, you don't have an alcohol peak, you don't have that weird little blip guy. You've got 2 peaks that are in this 3 to 4 range. That's a really good sign that you're dealing with an ether now. Our rules are going to be exactly the same as they were before. So we can go through. This is a CH2. This is a CH2. This is a CH. CH3. 2 CH3s. Kind of reading it left to right. Our 3 to 4 range. We've got 2 peaks. These are the 2 peaks that are going to be on either side of our alcohol, or sorry, our oxygen. Keep saying alcohol. So we have an ether. It's got 2 open positions right now. I can put a CH2 here and a CH2 here. Oh, I didn't fill these out. So 4, 3, 2, 1. I think this is another 9, 3, 2, 2, 1 here. Okay. This one is supposed to have 3 neighbors, so that would be a CH3. Gets rid of this one. This CH3 is supposed to have 2, so that works. This is supposed to have 1 neighbor, so a CH. And then that is supposed to have 9. It currently has 2, so 3 more can fill out this molecule. 4, so I kind of talked about ethers here. For ketones and aldehydes, they're a little bit different because you're a little bit further away or a little bit closer to a double bond. So if I think about these CHs here are directly attached to a single bond to oxygen. For a ketone, this is the carbon that's attached to the oxygen. It has no hydrogens on it, so it's going to give no signal. The signal is going to come from these 2 here, which are 1 away. So these end up in the 2 to 3 ppm range. They're not quite just a normal carbon bond that's like in the 0.5 to 2 range. They're a little bit further down. And then for an aldehyde, you have 1 carbon that's in that 2 to 3 range. So this is basically exactly the same as this here. But this one is a hydrogen or a proton that is directly attached to this double bond here. So that gets really shifted. And this ends up in the 9 to 10 ppm range. So I want you guys to do the next 2 NMRs, this one, and then on the next page, this one here. and then we will start class on Friday by doing these quickly, and then we will go through carboxylic acids and aromatic compounds, and then do some synthesis problems. All right, I will see you guys on Friday.